Hello, my name is Paul Geyer, and I'm here to chat with you today about cooling tower water treatment. This is what I'll be talking about today: the types of cooling water systems, cooling tower water calculations, objectives of cooling water treatment, microbiological deposits and control, corrosion in cooling systems, developing an effective cooling water treatment program, and cooling water system startup and layup requirements. By way of introduction, this is just a little bit about me and what I've been doing for the last few decades. First, the types of cooling water systems. Cooling water systems remove heat generated from a variety of industrial processes. There are three basic types of cooling water systems: once-through, open recirculating, and closed recirculating cooling water systems. This discussion will cover once-through and open recirculating systems only. First, once-through cooling water systems. Once-through cooling water systems use cool water that circulates only once through the entire system before being discharged. This type of system is commonly found along rivers or coastlines where abundant water is available for use. The system contains heat exchange equipment and transfer piping as indicated in Figure 1. Power utility services often use this type of system. Figure 1 indicates schematically a once-through cooling water system. Open recirculating cooling water systems are open to the atmosphere and continuously recycle and reuse the cooling water. These systems are composed of an evaporator unit, a cooling tower, or an evaporative condenser. These units mix air and water and allow some of the water to evaporate, cooling the balance of the water volume. The cooled water is then circulated to heat exchangers or chillers where heat is added to the cooling water, thereby removing heat from the process flow stream. The warmed water is then recirculated to the cooling tower where the cycle is repeated. Water is lost from the system primarily through evaporation. However, a portion of the cooling water must be discharged as waste, that is, blowdown, to maintain a suitable water quality within the system. All water lost from the system is replaced by makeup water. Recirculating cooling water systems are found in most air conditioning chiller operations as well as many heat exchange operations. Evaporative fluid coolers and evaporative condensers are terms defining open recirculating cooling water systems that use evaporators, which are slightly different than a cooling tower and do not send the cooled water out of the evaporative unit itself. An evaporative cooler cools a circulating fluid that does not change phase, that is, it does not condense from a gas to a liquid. An evaporative condenser cools a circulating fluid from a gas into a liquid, such as a refrigerant. The hot fluid that is to be cooled is brought to the unit. Figure 2 shows a typical evaporative cooler and evaporative condenser diagram. Figure 3 shows a typical open recirculating cooling water system, and Figure 4 shows a typical cooling tower system. Figure 2 is an evaporative fluid cooler and evaporative condenser schematic. Figure 3 is a schematic of an open recirculating cooling tower water system. Figure 4 is a schematic of a cooling tower water system. The types of cooling towers include natural draft, induced draft, and forced draft. In natural draft towers, airflow through the tower is achieved naturally, that is, without any mechanical means such as a fan. Air flows across the falling water and up through the cooling tower as a result of the differential density between the lighter, heated, and humidified air within the tower and the cooler and drier air outside. Fitting the tower with spray nozzles, which creates more mixing of air and water droplets and improves the evaporation efficiency, produces increased water cooling rates. Large utility power plants use these large natural draft cooling towers, which are called hyperbolic cooling towers due to their hyperbolic shape. See Figure 5. Figure 5 is a photograph of two large hyperbolic natural draft cooling towers. The term forced draft denotes that air is forced or blown by fans into the cooling tower and up through the flow of falling water in the cooling tower. Drift eliminators are installed to prevent water entrained in the air from leaving the system. The term induced draft denotes that air is drawn by fans through the flow of falling water and up and out of the cooling tower. The airflow can be drawn either cross-flow or counterflow with respect to the orientation of the falling water, resulting in either a cross-flow tower or a counterflow tower. Drift eliminators are also present. See Figures 6, 7, 8, and 9 for diagrams and photos of cross-flow and counterflow cooling towers. Figure 6 is a schematic of a cross-flow cooling tower. Figure 7 is a photograph of a cross-flow cooling tower. Figure 8 is a schematic of a counterflow cooling tower. And Figure 9 is a photograph of a large counterflow cooling tower. Cooling towers are commonly of the induced draft cross-flow variety, although counterflow and forced draft cooling towers are also represented. The cooling towers range in size from small to large capacity. Figure 10 shows a simple diagram of a one-fan induced draft cross-flow cooling tower. The major parts of the tower include the basin and cold well, louvers, fill, water distribution, and fan deck, drift eliminators, fan and fan discharge, and the end wall casings. Figure 10 is a schematic of an induced draft cross-flow cooling tower. The basin is that portion of the cooling tower structure located under the tower that is used for collecting cooled water and which can be used as a location for adding makeup water. The cold well is a deepened portion of the basin that contains submerged water circulation pumps. The basin may be constructed of concrete, wood, metal, or fiberglass. Louvers are flat or corrugated members constructed of wood, plastic, cement board, or fiberglass and installed across, horizontally, the open side of a tower. The main function of louvers is to prevent water from splashing out of the cooling tower through the openings where air enters the tower. Louvers are usually set at an angle to the direction of airflow. Fill is the internal part of a tower where air and water are mixed. The fill intercepts the downward fall of water. The water is mixed with the air contained in the fill material, and water is evaporated and cooled. There are two types of fill, splash fill and film fill. The falling water hits the splash fill, splashes, and breaks up into smaller water droplets, resulting in an increased rate of evaporation. The splash fill is made of wooden slats or bars, plastic, or ceramic tile. Film fill is a compact plastic material similar to a honeycomb that causes water to flow over the fill material, creating a large wet surface that maximizes evaporation as air travels past the film surface. Refer to Figure 11. Figure 11 is a photograph of high-efficiency cooling tower film fill. The drift eliminators efficiently remove droplets from the air and return the recovered water to the cooling tower, thereby minimizing the loss of cooling tower water. They are located in areas that are situated after the fill and water sprays and just before the area where the air exits the cooling tower. Refer to Figures 6 and 8. Drift eliminators are also known as mist eliminators. In a cross-flow cooling tower, the hot water basin is used to distribute the warm return water flow uniformly over the tower fill. See Figure 6. In a counterflow cooling tower, water sprays are used to distribute the warm water. See Figure 8. The fan deck supports the motor and fan of the water spray system. The stack is the structure, typically a cylinder, that encloses the fan and directs warm, humid discharge air upward and out of the cooling tower. A cell is the smallest subdivision of a large cooling tower in which the fan can operate as an independent unit. A mid-wall casing must separate each end of the cell from the adjacent cells to ensure all airflow induced by the cell fan is drawn only through the cell fill and mist eliminator air path. Figure 7 illustrates a typical 3-cell cross-flow cooling tower. Figure 9 illustrates a typical 4-cell counterflow cooling tower. Now some comments on some common cooling water system problems. Water-related problems can cause system downtime, loss of equipment efficiency, the need for capital replacement of equipment, and can increase the risk of disease from pathogenic microorganisms. An open recirculating cooling tower system has a greater potential for these problems than does a once-through cooling water system due to the air and water mixing design of the open recirculating system. These problems are associated with water-caused deposits, corrosion, or microbiological organisms and occur for various reasons. The cooling tower is essentially a huge air scrubber that can introduce materials such as microorganisms, gases, dust, and dirt into the circulating water, which provides an excellent growth environment for pathogenic microorganisms. These materials can contribute to the formation of deposits and cause corrosion. If the water is not properly treated and its quality maintained, corrosion in scale and solids deposition can occur. The potential for these problems results from the nature of the cooling system design and the operating conditions, including water evaporation, mineral concentration, and water temperatures of up to 130 degrees Fahrenheit. The constant addition of makeup water results in increased quantities of mineral constituents that can form scale deposits and corrosion. Blowdown control and proper water treatment can minimize these problems. The film fill contains small water and air passages that can become plugged, thereby causing a reduction in cooling tower operational efficiency due to reduced water evaporation. Current designs for heat exchangers and cooling towers provide for more efficient operation than in the past, but unexpected water problems may occur. Some of the more prevalent potential problems are described in further paragraphs. Now some comments on enhanced and super enhanced chiller condenser tubing. Recent air conditioning chiller equipment designs incorporate enhanced and super enhanced chiller condenser tubes. Previous designs have used smoothbore waterside condenser tubing. The enhanced tube is machined with rifled grooves that provide an increased surface area and a resultant increase in heat transfer. However, the rifled grooves and ridges tend to entrap dirt, silt, sand, and old corrosion products which are deposited from the cooling water as it passes through the tube. This deposition of material on metal surfaces can create a type of localized corrosion called under-deposit corrosion. This situation has resulted in numerous cases of tube failure. The super enhanced chiller tubes have even finer grooves and ridges, making this type of tubing even more susceptible to under-deposit corrosion. Refer to figures 12 and 13, which show photos of super enhanced copper tubes. Figure 12 is a photo of a super enhanced copper tube. And figure 13 is a close-up photograph of corrosion pitting on super enhanced copper tubing. Some cooling towers are constructed with galvanized steel components and must not be exposed to conditions of high pH, which of course is high alkalinity. The galvanizing process deposits a protective zinc coating on a mild steel metal surface, resulting in increased resistance to corrosion. Failure to avoid such exposure can result in production of white rust due to the corrosion of the galvanizing coating. Eventually, this corrosion process exposes the mild steel underneath, which then starts to corrode. White rust failures have been a common occurrence throughout the country, mainly with newer cooling towers. Proper protection of the galvanizing material is necessary both during startup of a new cooling tower and during normal operations. Specific water treatment chemicals are needed to provide this protection. Examples include pretreatment with a high level of orthophosphate. Small and medium-sized cooling towers use film fill, which is a tightly packed media as compared to the splash-type fill used prevalently in the past. Film fill has a higher potential for fouling, plugging, due to adherence and entrapment of biomass and dirt, silt, and sand. The cooling capacity of a cooling tower can be reduced if the film fill is extensively fouled. Instances of severe fouling have resulted in the collapse of fill into the cooling tower basin. In addition, fouling deposits in the fill can harbor pathogenic microbiological organisms such as Legionnaire's disease. Figure 14 is a photograph of a heavily fouled cooling tower film fill. With regard to Legionella bacteria, this type of bacteria is the cause of Legionnaire's disease. It can grow in cooling water systems even when a proper microbiological control program has been maintained. This bacterium can be discharged in the drift produced from all types of cooling tower systems. If a susceptible person inhales the bacteria, the disease could possibly develop. Due to increased awareness of cooling tower operators and the water treatment industry in general, the risk of being infected by Legionella pneumophila or other pathogenic microorganism from a cooling tower system is probably not much greater today than it was a few years ago. Still, a number of outbreaks of Legionnaire's disease are reported each year throughout the country. Now, a discussion of cooling tower water calculations. The principles of cooling tower system operations are that the function of the cooling tower is to dissipate heat from water-cooled refrigeration, air conditioning, and industrial process systems. Water is typically the heat transfer medium used to dissipate the heat. A cooling tower uses a combination of heat and mass transfer, evaporation, to cool the water flowing through the tower. Conductive heat transfer accounts for 20 to 30% of the total heat dissipated. The remaining 70 to 80% of total cooling is the result of evaporative cooling of about 1 to 2% of the recirculating water, depending on the decrease in temperature across the tower. It takes approximately 2,326,000 joules to evaporate 1 kilogram of water, that is 1,000 BTUs per 1 pound of water. If this amount of heat is extracted from 1,000 pounds of water, approximately 1 pound of water will be evaporated and the temperature will drop 1 degree Fahrenheit. If 10 pounds of water are evaporated, the water temperature will drop 10 degrees Fahrenheit. The water lost by evaporation is replaced with makeup water. Water is also added to replace water lost through tower drift, that is, loss of water from the tower as a fine mist, leaks in the system, unintentional blowdown, and water discharged as intentional blowdown. Water that is added to the cooling tower to replace all of these losses is known as cooling tower makeup water. With regard to the relationship between evaporation, blowdown, and makeup, the operation of cooling towers can be described by the relationship between evaporation, blowdown, and makeup. Makeup water must equal blowdown water plus water evaporation to maintain a constant operating water level in the system. Equations indicated on this slide illustrate this concept. One of the common terms used in describing the water use efficiency of cooling tower water systems is cycles of concentration, abbreviated COC. COC represents the relationship between the makeup water quantity and blowdown quantity. COC is a measure of the total amount of minerals that is concentrated in the cooling tower water relative to the amount of minerals in the makeup water or to the volume of each type of water. The higher the COC, the greater the water use efficiency. Most cooling tower systems operate with a COC of 3 to 10, where 3 represents acceptable efficiency and 10 represents very good efficiency. It has been found that the range of 5 to 7 cycles of concentration, COC, represents the most cost-effective situation. Calculation of COC by volume. If both makeup and blowdown water volumes are known, COC by volume can be calculated. The term is defined as indicated in the equations on this slide. Determining the COC by water analyses. To determine cycles of concentration COC, you must know the mineral content of both the makeup and blowdown water. For example, you must determine both the conductivity of the recirculating cooling tower water and the conductivity of the makeup water. Note that the blowdown water will have the same conductivity as the recirculating water. Conductivity is commonly measured in micromhos. You can also estimate COC by using other water quality parameters such as chlorides, silica, or sulfates. The relationship is represented by the following equation indicated on this slide number 39. Example 1, the measured conductivity of the blowdown recirculating water is 800 micromhos and the makeup is 300 micromhos. The cycles of concentration is calculated as indicated on this slide. Note that the parameters of conductivity or chloride concentration are used commonly for such measurements. Other water quality parameters can be used, but sometimes with inaccurate results. That is, calcium, magnesium, alkalinity, and silica can form deposits, meaning they drop out of solution. COC based on these parameters could be considerably less than that based on conductivity or chlorides. Similarly, chemical additions of sulfuric acid can yield higher sulfate levels than those species cycled up naturally. Controlling the cycles of concentration, a simple, sometimes overlooked rule. To increase COC, decrease blowdown. To increase COC, decrease blowdown. To decrease COC, increase blowdown. The relationship between COC and makeup. COC and makeup requirements are related to the temperature drop across the cooling tower and to the recirculating rate of the tower. As shown in figure 15, for a recirculating tower with water temperature drops of 10 degrees Fahrenheit, 20 degrees Fahrenheit, and 30 degrees Fahrenheit, the makeup water requirement decreases rapidly as cycles of concentration is increased to about 4 or 5, with lower incremental reductions at higher COC. Therefore, COC can be adjusted, increased, to allow for reductions in water use, water conservation, and for reductions in the amount of water treatment chemicals used. Figure 15 illustrates the effect of cycles of concentration on makeup requirements. The relationship between blowdown, evaporation, and cycles of concentration. You can use the cooling water evaporation loss to calculate the blowdown rate that must be maintained to operate at a selected cycles of concentration. The relationship between blowdown, evaporation, and cycles of concentration is represented by the equation and the notation illustrated on this slide. An example calculation is shown on this slide. A second example, a cooling system operates at 5,000 gallons per minute. The temperature drop through the tower is 14 degrees Fahrenheit. The evaporation estimate is represented by the equation indicated on this slide. For a cooling tower system serving an air conditioner and chiller operations, the evaporation rate used depends on the type of chiller. Approximately 1.5 gallons per hour per ton for centrifugal, reciprocating, and screw-type chillers, and approximately 3 gallons per hour for absorption-type chillers. Now comments on the objectives of a cooling water treatment program. The primary objectives of cooling water treatment are to maintain the operating efficiency of the cooling water system and to protect the equipment that contacts the cooling water. These objectives are accomplished by controlling or minimizing deposition, corrosion, and microbiological growth on the cooling water equipment. Treatment programs must also address requirements for environmental compliance, safety, water conservation, and limitation of chemical costs. This discussion reviews the requirements for and elements of a water treatment program for cooling water systems. First, deposit formation and control. Deposits that occur in cooling water systems are usually divided into two categories, scale and fouling. The presence of either type of deposit in the heat exchangers or in the film fill can interfere with heat transfer, thereby reducing the efficiency of operation. Deposits can also promote under-deposit corrosion. Scale and non-biological fouling are described in this discussion. Biological fouling is described elsewhere. Scale is formed from minerals formerly dissolved in water that were deposited from the water onto heat transfer surfaces or inflow water lines. As water is evaporated in a cooling tower, the concentration of dissolved solids becomes greater until the solubility of a particular scale-causing mineral salt is exceeded. When this situation occurs in an untreated cooling water system, the scale will form on any surface in contact with the water, especially on heat transfer surfaces. The most common scaling minerals are calcium carbonate, calcium phosphate, calcium sulfate, and silica, usually in that order. Formation of magnesium silicate scale is also possible under certain conditions. Most other salts, including silica, are more soluble in hot water than in cold water. However, most calcium and magnesium salts, including calcium phosphate and calcium carbonate, are more soluble in cold water than in hot water. This is called reverse solubility. The water temperature will increase as recirculating water passes through the cooling system. As a result, calcium and magnesium scales may form anywhere in the system, but most likely on heated surfaces, such as heat exchangers or surface condensers. Silica will form in areas having the lowest water temperature, such as in the cooling tower fill. Determining the scaling potential. The maximum solubility limit for specific dissolved minerals will determine the types of scale that can form under a given set of conditions. To minimize water blowdown, the amount of dissolved materials in the cooling water should be maintained as close as possible to the maximum solubility level. This quality parameter, TDS, is controlled by maintaining COC, cycles of concentration, in the system at a level that is equal to the lowest COC allowable for whichever salt has the lowest solubility. The salt of concern is often calcium carbonate or calcium phosphate, but it may be silica. The operating COC can be increased substantially with use of the cooling water treatment chemicals described here. With regard to calcium carbonate scale results from the breakdown of calcium bicarbonate, a naturally occurring salt. The degree of scaling depends primarily on the calcium levels, bicarbonate alkalinity levels, and water temperature in the cooling water system. The most accurate prediction of scale can be developed using the practical Pucorius scaling index, abbreviated PSI, not to be confused with pounds per square inch. A rough prediction of calcium carbonate scale potential can be developed using this formula, indicated on this slide. With regard to calcium phosphate scale results when calcium hardness reacts with phosphate. This will occur when more than 10 parts per million of orthophosphate are present in the circulating water and when the calcium hardness is sufficiently high. The following formula can provide a very rough prediction of the potential for calcium phosphate scale. And that is the equation indicated on this slide, number 53. Continuing on to the slide, number 54. Now, with regard to silica scale, silica scale can occur when the concentration of silica exceeds its maximum solubility limit in water. A safe, very conservative value to assume for the solubility limit is 150 parts per million as silicon dioxide. Thus, the maximum cycles of concentration can be calculated with this formula. However, silica solubility depends on pH and temperature and is in the range of approximately 150 to 180 parts per million as silicon dioxide at the temperature range encountered in most cooling towers, which is 80 to 130 degrees Fahrenheit. As the pH increases in the cooling tower water, silica becomes more soluble. Thus, if cooling tower water having a pH of 9.0, approximately 250 parts per million of silica as silicon dioxide is the maximum. Using 150 parts per million as the upper limit, the allowable cycles of concentration is represented by the following equation, indicated on this slide, number 56. Determining the cycles of concentration to control operations. In cooling water systems, the lowest calculated COC allowable as determined by the relationships for these salts is the controlling factor for operations. This is because as the system operates, the material that has the lowest calculated COC will be the first to come out of solution to precipitate and the most likely to form a scale deposit in the system. To prevent these materials from forming a deposit on cooling water equipment, you must keep the COC in the system at a level that is lower than the lowest COC calculated for calcium carbonate, calcium phosphate, calcium sulfate, and silica. Using approximate water treatment chemicals will allow higher COC, using appropriate water treatment chemicals will allow higher COC, depending on which chemical is used. Now, example number 3, a cooling tower makeup has the following composition indicated on this slide. At what COC can the system operate scale-free without water treatment? Assume that the estimated pH in the blowdown water is 8.5. The calculations are as indicated on this slide, number 59, based on calcium carbonate, calcium sulfate, and silica. The COC determined for calcium carbonate is lowest at 4.3, and this controls the system operation. If the system is operated without water treatment, scaling should not occur if the system is operated at less than 4.3 cycles of concentration. Use of scale control treatment will allow the number of allowable COC for calcium carbonate to be increased. You can then determine the COC and blowdown by using a calculated scaling index. For calcium carbonate scaling indices, the scale found most commonly in cooling tower water systems is calcium carbonate present in the form of calcite, calcium carbonate, limestone. The solubility of calcium carbonate, which decreases with an increase in temperature, is a complex function of temperature, total dissolved solids, calcium hardness, total alkalinity, and pH. To predict if scale would form in the hotter sections of a cooling tower water system, researchers have developed several scaling indices. Paragraphs describe the predictive indexes that are used most commonly for cooling water. Langelier and Riznar indices. Langelier derived a method to calculate the calcium carbonate scale forming and scale dissolving tendencies of drinking water. The method is based on determining the saturation pH at which calcium carbonate scale will start to precipitate out of solution. If the measured pH of the water is greater than its saturation pH, thus a positive value, the water has a scale forming tendency. If the measured pH of the water is less than its saturation pH, thus a negative value, the water will have a scale dissolving tendency. The pH actual minus the pH saturation is known as the Langelier index or Langelier saturation index, abbreviated LSI. LSI equals the actual pH minus the saturation pH. This index was originally designed to predict calcium carbonate scale in potable water. There are serious deficiencies in the accuracy of this index. Consequently, it has lost its practical application for cooling water systems. Riznar later devised a more sensitive formula for predicting calcium carbonate scale. This formula is known as the Riznar index or Riznar stability index, abbreviated RSI. The formula is 2 times the saturation pH minus the actual pH. A value of 6 indicates stable water, a value less than 6 indicates a scale forming tendency, and a value greater than 6 indicates a scale dissolving tendency. The indices have also been used to try to estimate the degree to which calcium carbonate scale will form in drinking water and in cooling water. The more positive the LSI value, the greater the scale formation. However, for the RSI, the smaller the index, the greater the scale formation. The LSI and RSI can give conflicting predictions based on the same water quality information. The practical Pacorius scaling index, abbreviated PSI. Pacorius and Brook developed a modified version of the RSI that gives a more accurate and consistent indication of the calcium carbonate scaling potential of cooling water. Known as the Practical Scaling Index, abbreviated PSI, and also known as the Pacorius Scaling Index. It takes into consideration the effect of the type of total alkalinity of the cooling water on the measured pH, the pH actual value. The measured pH does not always relate correctly to bicarbonate alkalinity because of the buffering effect of other ions. Rather than using the measured pH in calculating the PSI, an adjusted or equilibrium pH is used. PSI is equal to 2 times the pH saturation minus the pH equilibrium. As with the RSI, a PSI value of 6 indicates stable water and a value lower than 6 indicates a scale forming tendency. Without scale control treatment, a cooling tower with a PSI of 6 or 7 should operate scale free. However, a PSI of greater than 6 indicates that scaling may occur. Use of the PSI is most applicable when cooling water pH is above 7.5. Now some comments on scale control methods. Three basic methods are used to prevent the formation of scale in cooling water systems. First, remove the water scaling ingredients from the water before use. This includes softening and other technologies. Keep the scale forming ingredients in solution. This is the most common scale control method used for cooling water, and it can be achieved by use of either or both of the following two methods: adding acid, which lowers the pH of the recirculating water, or adding a scale inhibitor, such as a phosphonate or specific polymer, which allows higher COC, cycles of concentration, to be maintained without scaling. Acid neutralizes, that is, destroys mineral alkalinity, one of the constituents forming calcium carbonate scale. However, because of the hazards associated with handling strong acids and the potential damage from an acid spill, the use of acid in cooling towers is not recommended. Allow the water scale ingredient to precipitate as sludge. Modern chemical treatment can distort or modify scale crystals such that they cannot adhere to each other to form a hard deposit. Instead, they become a sludge that can be removed through filtration or blowdown. All three methods are authorized at various installations and can be used in combination with one another. With regard to calcium carbonate scale control using solubilizing chemicals, acids and phosphonates are chemicals that keep scale from forming. The use of acid in cooling towers may not be appropriate at some installations due to the associated risk of corrosion. Acids, the acid most commonly used is sulfuric acid, used as a diluted solution, 40% sulfuric acid in water. The use of acids requires adequate pH control. With regard to phosphonates, the phosphonates used most frequently for calcium carbonate scale control in recirculating cooling water systems are AMP, HEDP, and PBTC, and the full chemical names of these chemicals are indicated on this slide. They are rather complex. The chemical reaction of all phosphonates is similar, however their stability varies greatly. The presence of chlorine or other oxidants in treated cooling water favors the use of PBTC, which is very resistant to decomposition, followed by HEDP, and finally AMP. An active dosage of 3 to 5 parts per million of either AMP or HEDP, or 1.5 to 2.5 parts per million PBTC will increase the solubility of calcium carbonate by a factor of 3 or more relative to using no chemical treatment. Rather than operating at a PSI of 6.0, stable water, no scale, in an untreated system, the cooling tower water can be used at a PSI of 4.0 without the occurrence of scale. However, in the absence of calcium scaling conditions, phosphonates can increase the corrosion of both mild steel and copper. With regard to calcium carbonate scale control using solubilizing polymers, many different polymers are used in water treatment. For the most part, they have multifaceted performance capability. They can inhibit various types of scale formation as well as dispersed sand and silt and so on and so forth. Often water treatment products will include more than one type of polymer in the product formulation. For control of calcium carbonate, homopolymers such as polyacrylate, polymethacrylate, and polymaleate are used to keep calcium carbonate in solution. Dosages of 3 to 5 parts per million of active polymer in the cooling tower water can control calcium carbonate scale formation to a PSI value as low as 4.5. With regard to calcium carbonate scale control using sludge-forming polymers, certain homopolymers and copolymers act as crystal modifiers by distorting calcium carbonate crystals such that they do not attach themselves to heat exchange surfaces, but instead the crystals become solid sludges that can be removed through filtration or blowdown. Usually dosages of 1 to 3 parts per million of active polymer in the cooling tower water will control calcium carbonate scale. due to formation of sludge rather than the stabilization of carbonate in solution, the PSI is not meaningful under these conditions. With regard to calcium phosphate scale control using solubilizing inhibitors, often calcium phosphate scale is formed in cooling water systems treated with a phosphate-based corrosion inhibitor program, or when phosphate is present in the makeup water, i.e. potable or recycled water. Calcium phosphate is much less soluble in water than is calcium carbonate. If the calcium hardness is 500 parts per million and the pH is above 7.0, without any polymer treatment, calcium phosphate scale will likely form even at the low level of 10 parts per million as PO4 phosphate in the cooling water. Calcium phosphate solubility can be increased by a factor of a little less than 3 by the addition of the 4 parts per million phosphonate HEDP/PBTC, or by the use of 6 to 8 parts per million of a copolymer or terpolymer specific for calcium phosphate inhibition. Calcium sulfate formation can result from high concentrations of calcium ions and sulfate ions in the recirculating water. However, calcium sulfate is the most soluble of the scale-forming calcium salts found in cooling tower waters having pH levels of greater than 8.0. This means that calcium sulfate scale will not form unless some calcium ions, hardness, remain in solution after the calcium reacts with all the carbonate and phosphate in the water. Calcium sulfate scale may occur when the recirculating water contains calcium hardness in the range of 500 to 700 parts per million as calcium carbonate, and sulfate in the range of 500 to 700 parts per million sulfates. The addition of 3 to 5 parts per million of a copolymer of acrylate or acrylamide will allow calcium sulfate to remain in solution at a level almost 3 times the level allowed when using no treatment. Calcium sulfate scale rarely forms at pH levels above 8.0 in the cooling water. With regard to magnesium silicate scale control, formation of magnesium silicate is possible in cooling systems, but only under certain rare conditions. Magnesium ions, hardness, first react with hydroxyl ions, OH, to form magnesium hydroxide, which then reacts with, that is, absorbs, dissolved or colloidal silica. A deposit analysis often reports this material as magnesium silicate. Since magnesium hydroxide solubility decreases at pH levels above 9.0, this scale will usually occur only at a pH level above 9.0 and when the magnesium hardness concentration is greater than 100 parts per million. With regard to silica scale control, silica solubility is dependent upon temperature and pH. At pH levels greater than 8.5, silica remains soluble, so there is no scale, at a concentration of 250 parts per million as silicon dioxide. At pH levels of 7.5 or below, maximum silica solubility is 150 parts per million as silicon dioxide. At maximum silica levels, silica will first deposit on the cooling tower slats rather than in the heat exchanger because silica is more soluble in hot water than in cold water. The slats will become coated with a white, sometimes sparkling deposit. If this occurs, blowdown should be increased to decrease COC by at least 1 unit. This procedure should stop additional scale formation. If the concentration of silica in the makeup water is above 30 parts per million, it will usually be the parameter that controls the adjustment of cooling water system COC. If the silica concentration is high, external treatment can reduce the level of silica in the makeup water. The introduction of water treatment chemicals based on new polymer technology may allow the solubility of silica to be increased above the old recognized limit of 150 parts per million. Table 1 is a summary of scale control methods. The scales of interest are the calcium carbonate, calcium phosphate, calcium sulfate, magnesium silicate, and silica. Now, with regard to cooling water fouling, the term fouling refers to the deposition of materials that are normally held in suspension in the cooling water. Mud, silt, and other suspended solids brought into the system with the makeup water. Dust, dirt, and debris scrubbed out of air passing through the tower. Product leakage such as oils, corrosion products from the system, and biological organisms, both living and dead. Combinations of any or all these materials can be present in the cooling water. For fouling control from mud, dirt, and corrosion products, it can be controlled by the addition of a water-soluble polymer dispersant such as polyacrylate. The addition of about 4 to 5 parts per million of active polymer together with sufficient water velocity, around 3.28 feet per second, can keep foulants in suspension and prevent them from being deposited on heat transfer surfaces. Higher dosages in the range of 5 to 20 parts per million of active polymer can be required for heavily fouled systems. It's best to reduce the loading of suspended solids by mechanically removing them from the system through blowdown filtration and physical sump cleaning. Removing oil or oily materials requires a non-foaming surfactant. Elsewhere, there is a description of the prevention of fouling by biological organisms. Table 2 summarizes foulant control methods. And here on slide 78 is Table 2, which is a summary of the foulant control methods. With regard to microbiological deposits and control, microbiological organisms are composed of 3 classes: algae, bacteria, and fungus. Large biological organisms such as clams, snails, mussels, or similar species are referred to as macrobiological organisms. The presence of any biological growth can be detrimental to cooling tower operations. Problems include fouling, corrosion, and loss of efficiency. These problems can lead to downtime, higher operating costs, and even premature replacement of equipment. Additionally, some bacteria are pathogenic and can pose a risk to human life. Algae. The term algae refers to algal microbiological tiny stringy blue and blue-green plants, which are usually found growing in masses on top of and on sides of cooling towers. Algae grow only in sunlit areas. They will slough off and become part of the suspended matter in the circulating water, a situation which may cause fouling and plugging of water sprays. Algae also provide a breeding place and are a nutrient for bacteria. The term bacteria refers to a large group of one-celled microorganisms. Bacteria can grow in either the absence or presence of sunlight. There are several ways to classify bacteria, including aerobic, meaning those living in the presence of oxygen, and anaerobic, meaning those living in the absence of oxygen. In a cooling water system, one can categorize bacteria as either planktonic or sessile, which are terms that describe whether the bacteria are, respectively, either free-floating or found growing on surfaces, commonly referred to as stickers. Categories of bacteria are described below. The planktonic bacteria are suspended in the water, sometimes referred to as free floaters or swimmers, and are aerobic bacteria that thrive in an oxygenated environment. They are not harmful to the cooling system since they do not cause deposits or corrosion, but they can provide nutrients for other microorganisms, and in addition, some planktonic bacteria such as Legionella pneumophila are pathogenic and can present a significant human health risk. Sessile bacteria are called stickers or non-swimming bacteria and can cause deposits and corrosion. Sessile bacteria types include slime formers and anaerobic corrosive bacteria. Slime formers can grow and form gelatinous deposits on almost any surface in contact with the cooling water. These deposits can grow so large that they restrict water flow and interfere with heat transfer. They also may promote under-deposit corrosion. Feeling the sides of the cooling tower basin just below the water level is one way to detect the presence of slime formers. Usually, if there are slime formers in the system, you can feel deposits. Anaerobic bacteria thrive in oxygen-deprived environments and often establish colonies beneath slime deposits or under other types of deposits. One type of anaerobe is sulfate-reducing bacteria, abbreviated SRB, which produce hydrogen sulfide, a chemical that is very corrosive to metals. This type of corrosion attack is very localized and can result in pipe and tube failures. The presence of sulfate-reducing bacteria, SRB, should be suspected in a water system if the underside of a slime layer is black or if you detect the odor of rotten eggs. Any type of microbiological corrosion is referred to as microbiologically influenced corrosion, abbreviated MIC. Bacteria cause most of the MIC found in cooling water systems. Use surface microbiological measurements to monitor sessile bacteria. Table 3 indicates the bacteria types of interest and the problems that are created in cooling water systems. The term fungi refers to classes of organisms made up of molds and yeasts, some of which attack and cause wood decay in cooling towers. The control of fungi requires special preservative treatment of wood. Fungi also produce deposits in cooling water equipment. The term microbiological control refers to techniques used to minimize the presence of microbiological organisms in cooling water. Chemical biocide treatment is the method used on many installations for microbiological control in cooling water. Biocides that are used to control microbiological growth fall into one of two broad categories: oxidizing and non-oxidizing microbiocides. A cost-effective approach for control involves the regular use of oxidizers as a primary biocide, augmented by selective use of non-oxidizing biocides. Important factors for the effectiveness of any biocide include using a proper dosage and allowing adequate contact time with the microbiological organisms. All microbiocides are toxic and must be handled safely and with caution. With regard to the oxidizing biocides is a term describing microbiocides that oxidize or irreversibly burn up the bioorganisms. Oxidizing biocides also destroy nutrients that the microorganisms require for growth. Avoid addition of excessive overfeeding of oxidizing biocides, because they are corrosive to metal and wood in the cooling system and have the potential to destroy some scale and corrosion inhibitors. The various oxidizing biocides are described below. Chlorine and chlorine release agents. Chlorine compounds are the most effective industrial oxidizing biocides and the most widely used. Chlorine is available as a chlorine gas, dry calcium hypochlorite, liquid sodium hypochlorite, plus several other dry products that release chlorine. When chlorine is introduced into water, it hydrolyzes to form hypochlorite ion and hypochlorous acid. It is the latter chemical that is the stronger oxidizing biocide. The presence of hypochlorous acid is greater, proportionate to hypochlorite ion at low pH levels. At a pH of 5, hypochlorous acid exists almost exclusively. At a pH of 7.5, there are approximately equal amounts of hypochlorous acid and hypochlorite ion. Figure 16 shows this relationship. Chlorine is effective, but to a lesser degree as a biocide at a pH of 7.5 or greater, because the hypochlorite ion has about 1/10 the biocidal efficiency or efficacy of hypochlorous acid. A pH range of 6.5 to 7.5 is considered optimal for chlorine or chlorine-based microbiological control programs. Above pH 7.5, relatively higher levels of chlorine are required to be effective. Some installations seldom use gaseous chlorine for treating cooling water towers because of safety concerns, difficulty with controlling the feed of the gas, and increasing concern for the environmental effects of escaping residual chlorine gas. The most commonly used chlorine-based products are bleach and HTH. Table 4 indicates chlorine release agents. HTH is the calcium hypochlorite. Figure 16 indicates the relationship between halogen species and pH in water. Bromine release agents. Bromine compounds are very similar to chlorine compounds. Although more expensive than chlorine compounds, their main advantage is that bromine is more effective at higher pH ranges, 7.5 or greater, than is chlorine. Bromine has a lower vapor pressure than chlorine and is 6 times as soluble in water, making it less subject to vaporization loss from a cooling tower. When bromide is introduced to water, it hydrolyzes to form hypobromite ion and hypobromous acid. Figure 16 shows this relationship. A pH range of 7.5 to 10 is considered optimal for the use of bromine. Bromine release agents include dry chemicals called hydantoins and bromine salts, such as sodium bromide. When a salt solution is mixed with an oxidizing agent such as bleach and a reaction occurs, bromine is produced. In water, bromine degrades more rapidly than chlorine. Recent developments in bromine chemistry have resulted in the production of a bromine solution. Table 5 shows examples of some bromine release agents. The most popular sources of bromine are the dry bromine release agents. Table 5, indicated here on slide 91, indicates the bromine release agents together with some comments on their how they are available and their actions. Ozone is a gas produced by passing dry air either through a strong electric field or near an ultraviolet light. If ozone is dissolved in water, the resulting solution can be added to cooling water. Ozone is a very strong oxidizing biocide that, if properly applied, can provide effective control of microorganisms in cooling tower systems. However, because of safety and operational problems associated with its manufacture and use, and the resulting high capital and operating costs, it is neither the most economical method nor the preferred method for microbiological control in cooling towers under normal operations. Ozone can increase metal corrosion and does not prevent scale. Chlorine dioxide is a gas generated by mixing several chemicals. The chlorine dioxide gas produced in this manner is subsequently dissolved in water, with the water containing the chlorine dioxide then added to the cooling water. Chlorine dioxide must be produced in close proximity to the point of use. It is not recommended for use on some installations due to the complexity of its production and safety concerns associated with its production and handling. Hydrogen peroxide is a liquid that is usually used at a concentration of 30% in water. Hydrogen peroxide is considered one of the most environmentally friendly oxidizing biocides because it degrades to water. However, concentrated hydrogen peroxide will react in a violent manner when it comes into contact with organic chemicals and materials. The non-oxidizing biocides are microbiocides that act as poisons, if you will. They disrupt the metabolic or reproductive processes of micro and macroorganisms and are therefore toxic. Non-oxidizing biocides are organic compounds that are very toxic to organisms, including human beings and animals. They are usually liquids, but some are available as dry products such as pellets or other solids. A major consideration for their use is their persistence with respect to the discharge limitations for water, the effluent, containing these toxic substances. Also, when choosing and applying a non-oxidizing biocide, you must consider the cooling tower system's operating parameters such as pH and retention time. The applied dosages of microbiocides should never exceed EPA maximum limits, which are always printed on the container labels. The labels will also identify the active microbiocide ingredient, the percentage of each chemical that is present in the formulation, and the EPA registration number. Control programs often combine both oxidizing and non-oxidizing biocides. The most important aspect of biofouling control is to match the non-oxidizing biocide to the problem organism. Table 7 provides some guidelines for non-oxidizing biocide effectiveness. Table 6, indicated here on slide 96, provides the guidelines for oxidizing microbiocide effectiveness. The microbiocides: chlorine, bromine, ozone, chlorine dioxide, and peroxide, and the efficacy with different bacteria types, and then some comments of interest. Table 7 provides guidelines for non-oxidizing biocide selection. Algae control. Algae can be controlled by two techniques: chemical methods and physical methods. Since algae require sunlight to survive and grow, covering the upper hot water decks of cooling towers with plywood can often control algae deposits. Chemical methods consist of using oxidizing and non-oxidizing biocides, which can control algae to various degrees. Refer to tables 6 and 7. The effectiveness of oxidizers is considered only fair, while that of several non-oxidizers is in the range of very good to excellent. One of the more effective biocides for algae is terbutylazine, a triazine product. Bacterial control. Accepted industry practice for bacterial control is the use of oxidizing and non-oxidizing biocides that are specific for the type of bacteria. The most cost-effective microbiocide programs for medium and large cooling towers use an oxidizer as a primary biocide and one or more non-oxidizers selectively as a secondary biocide. Smaller cooling systems often use one or more non-oxidizing biocides, although dry oxidizing biocides are also used commonly. The most overlooked aspect of bacterial control is maintaining a system kept clean of deposits and suspended solids such as dirt, silt, sand, and corrosion products through the use of filters and periodic washdown procedures. Clean systems reduce the demand for chemical and microbiological control. Table 8 shows accepted industry guidelines for a bacterial control program with the use of a test kit. And Table 8 is indicated here on slide 100, guidelines for bacterial control in cooling towers. With regard to bacterial control with oxidizing biocides, bacterial control with oxidizing biocides can be accomplished by either continuous feed or slug feed of the oxidant. A continuous feed process typically maintains 0.1 to 0.3 parts per million of free halogen in the return water to the cooling tower. A typical slug-fed process adds treatment chemicals periodically to give 0.5 to 1.0 parts per million of free halogen in the return water to the cooling tower for a period of 2 to 4 hours 3 times per week. A typical slug feed process adds treatment chemicals periodically Halogen refers to the group of elements containing chlorine and bromine. Free halogen refers to the measured residual of halogen available for disinfection. Stabilized halogen technology is generally controlled on a total halogen residual. For continuous feed, control at 0.5 to 1 parts per million total, and for slug feed control at 2.4 parts per million for a period of 2 to 4 hours 3 times per week. Bacterial control with non-oxidizing biocides. Bacterial control with non-oxidizing biocides uses one or more biocides as shown in Table 7. Usually different non-oxidizers are added on an alternating schedule. They are slug-fed every other week for optimum effectiveness. Each time you use a non-oxidizing biocide, it is important to maintain an adequate dosage for 24 hours to enable sufficient contact time for maximum effectiveness. Legionnaire's disease is a respiratory disease that is caused by infection of susceptible individuals who have inhaled a fine water mist containing the bacterium known as Legionella pneumophila. Water in a cooling tower can become infected with the bacterium if an inadequate microbiological control situation occurs. The presence and density of Legionella pneumophila bacteria cannot be detected by standard microbiological testing methodologies. Instead, cooling water samples must be sent to a laboratory that has been certified to conduct the required tests. If the presence of the bacteria in cooling water is established, proper disinfection steps are required. A procedure known as the Wisconsin Protocol has proven effective. This protocol requires the addition of high dosages of chlorine, 10 parts per million free residual, at a pH of less than 7.5 for 24 hours, flushing the system and then repeating. Additional testing for Legionella is required to determine the effectiveness of the procedure. Maintaining a clean, microbiologically free cooling water system and using effective water treatment is preferable to dealing with remedial efforts. The Cooling Technology Institute and ASHRAE have published position papers on the prevention of Legionella, and these may be of some technical value. With regard to macrobiological control, the term macrobiological control refers to control of larger biological organisms such as mussels, clams, and snails. They can exist in cooling systems that use seawater or river water as makeup. The first line of defense is using mechanical prevention with strainers and filters on the intake water to prevent infiltration into the cooling water system. Control methods within the cooling system include thermal shock and chemical treatment with oxidizing and non-oxidizing biocides. The term corrosion in a cooling water system is defined as the electrochemical deterioration of a metal that is in contact with cooling water. Corrosion occurs when an electric current flows from one part of the metal, the anode, through the water, the electrolyte, to another part of the metal called the cathode. Corrosion takes place at the anode only. The cathode is the driving force of the corrosion action. Forms of corrosion associated with industrial water systems are illustrated in Figure 17. Figure 17, forms of corrosion, are indicated on this slide. 106, galvanic corrosion, crevice, deposit, general corrosion, and pitting attack. With regard to galvanic corrosion, the term refers to corrosion that occurs when two different metals are coupled together. The metal with the least resistance becomes the anode and will corrode due to the electrochemical reaction produced. One of the most common instances of galvanic corrosion occurring in cooling water system results when mild steel and copper alloy metals are brought into contact with one another. Copper tubing, for example, attached to a mild steel tube sheet, or brass valves connected to mild steel or galvanized piping. As a result of the electrochemical reaction, the copper is dissolved in the water and corrosion of copper alloy results. The copper can also plate out on mild steel surfaces setting up additional galvanic cells. Another example is the electrochemical reaction that occurs when mild steel and zinc, such as in galvanizing, are coupled together at temperatures normally found in cooling tower systems. The zinc becomes the anode and is corroded. Any coupling of a metal that is higher in the galvanic series with a metal or alloy that is lower in the galvanic series results in electrochemical reaction in which the higher metal functions as the anode or active metal. The term general corrosion refers to uniform corrosion of metal surfaces. A single piece of metal will have cathodic and anodic areas due to differences in impurities and stresses. These areas will change periodically, causing the metal to corrode over the entire surface at a more or less uniform rate. When two pieces of the same metal are in a solution capable of acting as an electrolyte and the electrolyte contains different substances or the same substance in different amounts, such as a salt or a mixture of salts or oxygen, an electrical potential difference will develop between them. The term crevice corrosion refers to corrosion that occurs in a slight separation between two pieces of metal, such as at the contact point of two mild or stainless steel plates that have been bolted together. Water flow is restricted in a crevice, and as a result oxygen is consumed faster than it can be replenished. The metal in the crevice functions as an anode and corrodes. This is a form of concentration cell corrosion, also called differential oxygen cell corrosion. Stainless steel is particularly susceptible to this type of corrosion, which results in localized or pitting attack. Figure 18 indicates the galvanic series of common metals and alloys found in cooling water systems. Most active, magnesium, zinc, etc., etc. Moving down, you begin to get into the irons and steels, and then down at the bottom are the noble metals, silver, gold, platinum, that where they don't corrode. Under deposit corrosion, the term refers to corrosion occurring under any type of deposit. The underside of a deposit that has been caused by fouling, bacterial slime, or debris acts in much the same way as the inside of a crevice. The metal under the deposit becomes anodic and corrodes. This process is considered another form of concentration cell corrosion because oxygen cannot easily get under the deposit. All metals are susceptible to this type of corrosion, which results in localized or pitting attack. Microbiologically influenced corrosion, abbreviated MIC. This term refers to metal corrosion associated with microbiological organisms whose presence contributes to the creation of or maintenance of a corrosive environment. MIC can be either eliminated or prevented to a large degree by the proper use of biocides. The term corrosion rate refers to the rate at which the corrosion action proceeds. The rate is measured in units of mils per year, abbreviated MPY, which is 1/1000th of an inch. The rate measurement is performed using corrosion coupons that have been exposed to cooling water for a short period of time, typically 30 to 90 days. The weight of the coupon is measured before and after exposure to the water. The thickness of the metal lost due to corrosion over the testing period is then calculated using a measurement of the weight loss. The weight loss is extrapolated to give a rate for 1 year, and a calculation of the thickness loss is then performed and the value is reported. Alternatively, this measurement can be taken using specialized instruments that rapidly measure corrosion rates. Table 9, indicated here on slide 113, indicates assessing corrosion rates in cooling water systems using a 90-day corrosion coupon test. Corrosion control methods in cooling water systems. Two basic techniques are used to provide corrosion protection to the metals that the water contacts: use of chemical corrosion inhibitors and raising the pH of the cooling water. Figure 19 illustrates the effect of pH on the corrosion rate of mild steel. Many cooling water systems contain components fabricated primarily of copper alloy and mild steel. Galvanized steel is present in galvanized cooling towers, and stainless steel may be present in piping. As the cooling water pH is increased, ideally to within the range of 8.0 to 9.5, copper and mild steel corrosion rates will decrease as indicated in Figure 19, although very high pH levels are corrosive to copper. The increase in pH alone cannot always protect metals adequately, especially since cooling water is highly aerated, oxygen saturated. Chemical corrosion inhibitors are used to provide protection from corrosion of the metal components of cooling water systems. Table 10 shows criteria for the selection of corrosion inhibitors. The principal strategy for a cooling system corrosion protection program is to ensure protection of the metal in the heat exchanger, the metal that is the thinnest metal in the system. The secondary goal is to provide protection from corrosion of the mild steel piping. When galvanized steel cooling towers are part of the cooling system, specialized corrosion inhibitors are the best control method. Galvanized steel is corroded at pH levels above 9.0 and below 6.0. Figure 19, indicated here on slide 116, indicates the effect of pH on corrosion rate of unprotected mild steel in water. Table 10, indicated here on slide 117, indicates the criteria for corrosion inhibitor selection of different types. Effective corrosion control requires maintaining appropriate pH levels, plus adding maintenance dosages of chemical corrosion inhibitors. Chemical corrosion inhibitors form a protective film or barrier on the cooling system metal surfaces that have been cleaned prior to adding an initial high dosage of inhibitor. The initial high dosage of inhibitor passivates or protects the metal. The appropriate dosage of corrosion inhibitor must be maintained continuously in the cooling water system to ensure continuing protection. Table 11 shows examples of various passivation and maintenance dosage levels of corrosion inhibitors. Corrosion inhibitors are divided into three classes: cathodic, anodic, and general filmers. Corrosion inhibitors form a protective film on either the anode, the cathode, or over the entire metal surface. The type of corrosion inhibitors are described below. The anodic inhibitors form a protective film coating on the anodic metal where the metal is lost, and thus directly control corrosion by preventing the reaction that results in corrosion. Any unprotected areas will corrode at a much faster rate than the protected areas, a factor that could result in pitting or localized attack of the unprotected areas. Examples of anodic inhibitors include orthophosphates, nitrite, and orthosilicates. Under certain conditions, molybdate can function as an anodic inhibitor. The cathodic inhibitors form a protective film coating of the cathodic metal where metal is not lost, and thus indirectly prevent corrosion by interfering with the current flow required for the electrochemical reaction to proceed between the cathode and anode metals. The corrosion reaction rate is governed by the size and type of the cathode relative to the anode. Even when cathode areas are not completely covered by the protective film, corrosion will occur, but usually more slowly and uniformly than when using anodic inhibitors alone. The occurrence of localized corrosion or pitting attack is greatly reduced. Examples of cathodic inhibitors include zinc salts, polyphosphates, and polysilicates. Under most conditions, molybdate will function as a cathodic inhibitor. General inhibitors produce a protective film on the surface of all metals. These corrosion inhibitors are organic compounds such as certain phosphonates, amines, and other nitrogen chemicals. They can be used in cooling water systems. Corrosion inhibitors for specific metals. Some corrosion inhibitors provide corrosion control for specific metals. The protection of copper and copper alloys requires the use of azoles such as talitriazole, TTA, BZT. These are all fascinating chemical names which you will certainly want to review at your leisure, which can be added to the system separately from or as part of a blend of other treatment chemicals. Galvanic or crevice corrosion. Control of galvanic or crevice corrosion is achieved primarily by engineering and mechanical design. These types of corrosion can also be partially controlled by physical and chemical considerations. A dielectric coupling insulator used to separate two different metallurgies can help to prevent galvanic corrosion. From a chemical perspective, adjusting pH and using proper corrosion inhibitors will reduce corrosion. For deposit corrosion, this requires maintaining deposit-free metal surfaces. It applies to any form of deposits such as scale, biomass, corrosion products, or foulants. The occurrence of these types of deposits is prevented by dispersants, scale inhibitors, or biocides, along with the maintenance of adequate flow velocities. Routine, adequate cleaning of filters and tower sumps will help reduce deposits. MIC is best prevented by stopping conditions that foster biological growth by using an effective microbiological control program. A MIC prevention program includes adequate control of deposits and fouling, avoidance of low flow and dead-end conditions, and implementation of consistently effective microbiological control program. Table 11, indicated here on slide 123, shows the guidelines for passivation, film formation, and subsequent maintenance for selected corrosion inhibitors, their dosages, and film formation times. Now, some remarks on developing an effective cooling water treatment program. An effective and complete cooling water treatment program addresses many factors, including those associated with compliance and safety and protection of equipment and cost. Compliance and safety considerations are mandatory components of the program. Achieving or exceeding minimally acceptable equipment protection at the lowest possible cost is an advisable outcome for a well-designed program. The overall cost of the treatment program includes not only the cost of chemical treatment, but also the costs of water, disposal, manpower, and equipment. Development of an appropriate cooling water treatment program is dependent upon knowledge of both the specific equipment to be protected and the quality of the water to be used, the source water and the system water. Corrosion inhibitors are selected based on the metallurgy of individual pieces of cooling system equipment. Typical systems include equipment components of different metals. For example, systems may include smooth and enhanced copper tube bundles, mild steel transfer piping, and galvanized cooling tower components. Therefore, to select the proper corrosion inhibitor, it is important to identify all metals contacted by the cooling water. See Table 10 for corrosion inhibitor selection criteria. Operational features and parameters of the cooling water system must be known to select the proper scale and deposit inhibitors. This requirement refers to operational parameters such as maximum temperature, minimum velocities, usage patterns, and whether or not layup periods occur. The best chemical treatment programs cannot overcome the stresses of poorly operated systems. A good example of system stress is intermittent chiller operation that allows for suspended solid accumulation deposits in chiller tube surfaces due to low flow or lack of flow. This situation creates a strong potential for underdeposit corrosion and for MIC that the chemical treatment may not be able to overcome completely. Stagnant water can also cause deposits and corrosion. High water temperatures can cause scale. The maximum water temperature should be known so that the proper scale control method can be used. Water quality within the cooling water system is a critical consideration. The source may be potable or reuse or recycled water. The various water constituents must be known, so appropriate water treatment chemicals can be selected for controlling specific water quality parameters. With regard to cooling water treatment programs, the categories for the purpose of developing a water treatment program, cooling tower recirculating water systems, can be divided into three basic categories. Small-sized towers, capacity less than 25 tons, medium-sized towers, 25 to 100 tons, and large towers over 100 tons. The water treatment program selected for cooling tower systems will vary depending upon the size of the tower as well as other factors. Treatment program considerations are further described for small, medium, and large size towers. The cycles of concentration of small, medium, and large cooling towers may be controlled by blowdown, either automatic or manual, to avoid the high levels of silica and calcium salts that can lead to scale. If the cooling tower is not chemically treated, the cycles of concentration should be adjusted to be slightly less than the lowest allowable COC value based on all scale-forming water ingredients. The use of chemical treatment permits a higher COC, which is usually limited by either the chemical effectiveness or the water treatment control. An example, an untreated cooling tower system can operate at 10 cycles of concentration based on the level of silica without scale forming, but can operate at only 2 cycles of concentration based on the level of calcium carbonate. Accordingly, the tower system should be operated at a maximum of 2 COC. The system can likely be operated at 5 to 6 COC when an effective chemical treatment is applied and maintained to control calcium carbonate. With regard to treatment programs for small cooling towers, typically a small cooling tower will have a rating of less than 25 tons. The treatment program used for small towers should be designed to be simple to control and easy to apply, with very little operator attention required. This does not mean that no attention is required, only less than that required for medium-sized systems. The treatment program for small systems is indicated in Table 12, which is on this slide 130. Treatment. Small systems can be treated with a low dosage, 5 to 10 parts per million, of a slowly soluble phosphate chemical, sodium calcium polyphosphate, by placing a nylon mesh bag containing the product into the cooling tower. The product, if applied in this manner, will usually provide adequate scale and corrosion control. Microbiological control can be obtained by use of a dry pelletized oxidizing biocide. Either of these biocides can be fed continuously via a feeder or suspended in a mesh bag in the cooling tower water. The cooling tower sump should be kept clean of suspended solids and other debris by use of a filter and periodic washdowns. Testing is usually limited to assurance that the optimum COC value is being maintained and that the chemical treatment agents are present in the water. The bag with the chemical treatment should not be allowed to become less than 1/2 full. The frequency for refilling the bag will vary. Once every 1 to 2 months is typical. Initially, the treatment level should be checked to ensure that adequate but not excessive levels of both phosphate and the biocide are present in the cooling water. For large and medium-sized cooling towers, the chemical treatment program typically requires sufficient regular testing as well as water and chemical control to protect the equipment in contact with the cooling water. Usually, treatment includes control of scale, fouling, microbiological growth, and corrosion. The composition of an optimum chemical treatment program for cooling towers on a typical installation depends on the quality of water available, the operating conditions of the cooling system, and the environmental constraints placed on treatment chemicals in the blowdown water. Conditions at particular installations may require variation of the quantity or the mix of chemicals suggested in Table 13. Medium and large cooling towers are usually but not always treated with a liquid formulation containing both scale inhibitors and corrosion inhibitors. These are often simply referred to as inhibitors. Inhibitor products are usually fed on a continuous basis using automated control and feed equipment. The concentration of these formulated products varies greatly from vendor to vendor. Biocides are usually but not always liquid products. It's common to use an oxidizing biocide as a primary biocide and a non-oxidizing biocide as a secondary biocide used as needed to control bacteria and other biological growth. Oxidizing biocides can either be fed continuously at a low level or dosed periodically at a higher level. Non-oxidizers are dosed as needed and only when oxidizing biocides are either ineffective or not used at all. Table 13 here on slide 135 indicates treatment programs suggested for medium and large cooling towers. Testing should be done regularly to ensure that the COC chemical levels and bacteria levels are within the targeted control range. This requirement could demand a testing frequency of 3 times per week or even daily. Some comments on the cooling tower operator duties. If detected early, problems associated with scaling, corrosion, and fouling in a cooling tower system can be minimized by corrective action. Some of the things the operator should look for when on site are described below. First, cooling tower distribution deck. It's important to look for the presence of algae, debris, or anything that has plugged water distribution holes, causing an uneven water flow through the tower, thus lowering tower efficiency. Clean plugged holes and replace damaged water distribution spray nozzles. In addition, look for the presence of algae deposits. If algae deposits are present, increase the level or frequency of biocide or algicide treatment and cover the deck if uncovered. The presence of scale deposits, particularly on cooling tower fill, can be established by removing some fill to determine if partial plugging has occurred. Scale can range in color from white to gray or reddish depending upon the scale composition. Scale formation on the cooling tower fill usually indicates a severe scaling situation. If possible, obtain a sample of the scale for analysis and based on the results, select a scale inhibitor for that specific scale. With regard to scale deposits on air intake slats, this buildup is due mostly to water splashing and evaporating, causing deposition of soluble salts or minerals. This situation does not indicate a serious problem. These deposits can be and should be washed off periodically, but ideally not into the cooling tower basin. Chemical treatment can provide some reduction in the occurrence of deposits. Slime deposits can sometimes be detected by feeling below the water level on the distribution deck and on the walls of the cooling tower basin. Most microbiological growth will have a slimy feel. If slime deposits are present, increase biocide frequency or increase the dosage. With regard to suspended solids, the purpose of a dispersant is to keep particulate solids in suspension and to prevent them from settling or from adhering to heat transfer surfaces. Adequate water flow is required to prevent them from settling. Particulate solids in suspension are removed with the blowdown water. The tower water should be turbid if the dispersant is doing its job. Keep the cooling tower sump clean of suspended solids by cleaning periodically and using a filter. When removing corrosion test coupons, always note and record the visual appearance with regard to the presence of scale rust or biomass. Take photographs of the corrosion coupons. Submit or evaluate coupons for corrosion rate and for the type of corrosion that is occurring. To effectively examine the inside water-contacted surfaces of heat exchanger tubes, a borescope is needed because only a few inches of the interior can be seen visually using a flashlight. Scale deposits, typically hard and tightly adhered to the tube surface, range in color from white to gray or reddish, depending on the composition of the scale. No scale should be present. It's important to inspect heat exchanger tubes at least once a year. Fouling type deposits may look similar to scale deposits. Unlike scale, these deposits usually adhere loosely to the tube surface. Biomass will appear slimy and feel slippery and will usually adhere loosely. Degradation of chiller performance or chiller efficiency may be a strong indication of scale or fouling problems in the chiller. If a reduction in chiller capacity occurs while cooling water is being cooled efficiently and within design parameters, then the chiller condenser section should be opened and examined. The chiller evaporator section may not contain water material scale but may be fouled with corrosion products. You should open and examine the chiller evaporator if chilled water could possibly be inadequately treated. Cooling towers made of galvanized steel should be examined for white rust or possible rusty surfaces that may indicate that the galvanizing is no longer present on the metal surfaces and the steel is rusting. Cooling towers constructed of wood should be examined for wood deterioration or decay. The startup of a new cooling water system requires special consideration. Proper cooling water system layout is also important, especially for chiller tube bundles or other heat exchange equipment. For a new cooling tower system, it's important to make sure that the equipment that contacts the cooling water is clean and properly protected from initial corrosion. Also, disinfection is needed to eliminate the presence of microbiological organisms that can cause corrosion, deposits, and growth of pathogenic organisms such as Legionella bacteria. Implementation of a proper layup process is critical to prevent corrosion and microbiological growth during stagnant water conditions. The term standby is often applied to a chiller that is in rotation with other chillers online. This standby period could be of varying duration from a few days to a few weeks. Rotating chillers frequently is important for minimizing stagnant conditions that lead to underdeposit and MIC corrosion. It's good practice to run the recirculation pumps through a standby chiller for at least 15 minutes each day to minimize corrosion. A chiller that must be left on standby for an extended period of weeks without recirculation should be laid up wet or dry according to procedures described. Common problems that occur during layup or due to improper initial startup include corrosion of tubes and transfer piping, sometimes to the point of failure, microbiological growth with potential for MIC corrosion, and growth of pathogenic microorganisms. With regard to the startup of new cooling water tower systems, the initial cleaning. A new cooling water tower system will contain dirt, oils, greasy films, and rust located on the metal surfaces as a result of system fabrication. A pre-operational alkaline cleaning process is required to remove the dirt, oil, grease, and rust, and to prepare metal surfaces for initial corrosion control. When galvanized steel is involved, special care must be taken so that the pH does not exceed 8.5 during the cleaning and passivation process to avoid conditions that promote white rust. The cleaning and passivating procedure for a new cooling tower system is usually part of a new system construction project and as such is not in the direct control of the cooling system operations personnel. Verification of the completion of these important steps is obtained from the contracting officer involved with the project. A cleaning and passivation procedure for cooling tower systems with galvanized steel is provided below. The procedure is similar for systems that do not contain galvanized steel, except that the pH restriction does not apply. In the startup of new cooling tower systems containing complex metallurgies that include galvanized steel, follow the cleaning and passivation procedures for cooling tower systems containing galvanized steel, stainless steel, mild steel, or copper. These procedures should not be used for cleaning and passivating aluminum. Conventional chemical cleaners and typical heating, ventilation, and air conditioning water treatment programs use highly alkaline, high pH water, which can initiate white rust formation on galvanized surfaces and copper tubes. Galvanized steel can simply be passivated by exposure to highly aerated water and a phosphate or polysilicate treatment. This treatment forms a zinc corrosion inhibition layer, which is a natural, dense, adherent, and positive corrosion product film. High pH above 8.5 produces unwanted white rust that is fragile and not protective against corrosion. The following procedures are recommended. For hydrostatic testing, and perform hydrostatic testing by inspection and removal of all debris. Fill the system with treated water and circulate. This should include orthophosphate or hexametaphosphate at 40 to 60 parts per million and totyl triazole, complex term there, at 10 to 20 parts per million. Pre-operational cleaning procedure. If the system passes hydrostatic testing, proceed immediately to this pre-operational cleaning and passivation procedure. Do not allow untreated water to be added to the system. Drain and flush any debris from hydrostatic testing. Dose and circulate for 24 hours a sufficient amount of a cleaning formula based on the volume of the system. Drain and flush the system and clean all strainers. Fill the system with makeup water and circulate for 30 minutes. Take a sample of system water while it is circulating. The sample should match the makeup water supply for clarity and suspended solids and have a conductivity with pH of plus or minus 10% and pH from 7.5 to 8.5. If necessary, repeat steps A through E until the system water matches this description. The system should now be clean and passivated. Chemical cleaning and passivation formulation. Apply this chemical cleaning and passivation formulation when the water system pH is 7.5 to 8.5. Formulation limitations may require separate components to keep things in solution. Other formulations may be used, and the chemicals to be employed are further indicated on this slide. Supplemental corrosion inhibitors may be used in conjunction with the phosphate but are not required. Maintain and circulate the levels for the time required. After passivation, proceed to operational readiness or layup as required. Tables indicate chemical technology used for passivation. If system operation is not required for a period of a week or more, proceed to layup. For normal operation, allow corrosion inhibitor levels to subside to maintenance levels through normal blowdown. Proceed to maintenance water treatment program. Tables 14 and 15 on slide 151 indicate the required chemical technology involved and the supplemental chemical technology involved. For layup of cooling tower systems, wet layup systems and system equipment such as heat exchangers, chiller tube bundles, and the like can be laid up wet, but first they require a physical cleaning to remove all suspended materials. Apply corrosion inhibitors at increased dosages, usually at a level of about 4 to 5 times the normal maintenance dosage. Apply an increased dosage within EPA limits of a non-oxidizing biocide that has a long half-life. Dry layup systems and equipment can be laid up dry, although dry layup is more appropriate for a single piece of equipment such as a chiller's condenser tube bundle or other heat exchanger. All metal surfaces must be completely dry. Residual moisture is not acceptable. In humid climates, you should use a desiccant such as a quicklime gel or an equivalent. Place the desiccant in as many locations as necessary and replace as required. And this brings us to the conclusion of this brief discussion of treatment of cooling tower water systems. I hope this has been of some interest to you. It was about what you were looking for, and will help you to address cooling tower water treatment issues as they come across your desk from time to time in the future. With that, again, thanks a lot for letting me chat with you, and have a nice rest of the day.